So in this video, we're going to estimate the cost of the secondary machining done to this extruded stanchion plate. So in my previous video, we estimated the cost of this extrusion itself, and we estimated that cost to be about $2.30. So that was without all of the secondary machining operations that are required. And that's what we're going to do in this video. So we're going to estimate the cost of all of these secondary machining operations that are needed. So built into our DFM concurrent costing software, we have two different methods to estimate machining costs. And in this video, I'm going to demonstrate the most detailed method of the two. So this method is actually quite different than most other machining cost estimators that are on the market, because it enables you to get very detailed breakdowns of the machining times and costs for your parts. And I think that'll become quite apparent as we go through this detailed analysis today. So after extrusion is done, then we're going to add a machining tool setup. So I'm going to insert this vertical machining center. And then I'm going to drill 4 holes in the part to form the stanchion holes that are on the finished part. Then I'm going to use a finish milling operation around the circumference of each hole to clean up those holes and make them nice and round. So I'm going to add a peripheral end milling operation. And then I'm going to drill 2 holes for the securing screws that are in the part flange. And then I'm going to mill 2 slots for the screws that are in the opposing part flange. So I'm going to rough multiple slot end mill. And then I'm going to mill a slot into the flange of the part, which will become the rectangular hole that's in the finished part. So I'm going to do a rough single slot end mill. So that milling operation is going to result in a hole that has rounded corners. So in order to square those corners off, I'm going to add a broaching operation. So first I'm going to add this Pioneer VT315 broaching machine, and then I'm going to broach a slot into that part. So now that I've defined all of my machining operations, I'm going to go back and define all of the cut dimensions for each individual operation. So for these stanchion holes, I'm going to use a carbide drill, and the holes that I'm going to be drilling, they are represented by this diameter, so the diameter of that red edge that I've shown or indicated. And then the length or depth of my holes, I'm going to indicate them as that edge shown there in red. And I'm going to be drilling 4 of these stanchion holes in my part. So after I've defined those parameters, the software goes to its library of materials and it gets the recommended cutting speed and feed for this operation that I've defined. It uses those properties along with the properties of this machine that I've chosen to calculate the productive time as well as the non-productive time for drilling the 4 holes. So here, the software has estimated 12 seconds of machine time to drill the 4 holes. For the cleanup milling around the circumference of those holes, I'll be using a solid carbide tool. And for the width of that surface, that would be defined as that dimension there. shown in red. And then the length of the surface to be milled is going to be the circumference of a hole. And that would be indicated here as shown in red. And then I'm going to be milling around all four of those features. I think I'll be using a rather small end mill for this operation. So I think I'm going to be using maybe 1/4 of an inch end mill or so. So I think I'll, specify a tool diameter of about 6 millimeters. I think that's quite reasonable. So now the software uses the minimum cost machining properties for this operation, as well as the properties of my machine, and it estimates the machine time at 17 seconds. And that's for all 4 holes. So what we've learned so far is that producing these 4 finished stanchion holes on this extruded plate, they require, for the drilling, it's about 12 seconds, and then for the, milling around the circumference of all the holes, that's about 17 seconds. So it's about 29 seconds of machine time. So that's all of the machining time, as well as the non-productive time on the machine. So for drilling the screw holes in the flange, I'd like a carbide cutting tool. And I'm going to define this diameter, the diameter of that edge shown in red. That's the diameter of the hole I'll be drilling. And then the depth of the hole that I'm going to drill is shown here, indicated by that red edge. So those screw holes, they take about 8 seconds to produce. For milling the screw slots, so I'd like a solid carbide tool. And for the width of that surface, I'm going to define that surface as the distance between these 2 points that I've indicated, here shown in red. So that is the width of the slot that I'm going to be milling. And for the length of the surface I'm going to mill, the length of my slot, I'm going to indicate that here, shown in red. And then for the depth of my slot, that's that dimension, shown in red. So these slots, they take about 8 seconds to produce. So for the larger flange slot, so I'm going to use a different tool, and I'm going to use a solid carbide end mill to produce the slot. And then the width of my slot is going to be that width, indicated in red. And now the length of my slot is that length. And then the depth is that dimension, shown in red. So that large slot takes about 6 seconds to produce. So now for the broaching operation. The width of my slot is that width, shown in red. And then the depth of my slot So the previous milling operation is going to leave these rounded corners inside this slot. And what we'd like to do is broach those corners square. So the depth of my broaching operation I'm going to define using these 2 points. So it's roughly from there to about there or so. So the depth that I'm going to be broaching is roughly the distance between those 2 points that I've identified on the CAD model, shown in red. So that broaching operation takes 31 seconds to perform. And we're going to be repeating that broaching operation on the other end of that flange slot. So I'm just going to make a copy of this first broaching operation. And I'm going to paste it back onto that same machine. So now that finishes the analysis of the secondary machining on this extrusion. So the milling and drilling operations, they cost just about 92 cents. And then the broaching operations, they're actually quite a bit more expensive at about $1.28. So the sharp corners on that flange slot, they actually end up being a pretty major contributor to the cost of this part. And if you were interested in a redesign of this part to reduce its cost, then elimination of those sharp corners and these broaching operations that are required because of those corners, they would certainly be one area that would be worth investigating. So now we've estimated the total cost of this part, and we've estimated the cost of the part to be about $4.50 or so. And now that we've done that, we're able to compare this extruded stanchion plate with the other designs. So I've analyzed the other stanchion plates in this analysis file. So this analysis that I've just opened up, this one right here, it's identical to the analysis that we just completed together. So the total cost, as you can see, it's about $4.50. And this is analysis that's identical to the one that we just did. So this second tab, it contains a total cost analysis of the cast stanchion plate. You can see it looks like that. And then the third tab contains the fabricated plate. So just quickly, we can open up this cost versus life volume graph, and we can compare the three designs using this graph. So on this graph, this horizontal axis down here, that's the life volume. So that's the total number of parts that are produced. And the vertical axis is the total cost per part, and it includes the amortized cost of any tooling that might be required. So we're going to compare all three designs, the extruded plate, the investment plate, and as well as the fabricated plate. So these curves here that are shown in this graph, they show how the total cost per part varies if production were stopped at each life volume. And the most interesting aspects of this comparison, they occur at these crossover points. So, not so surprising at lower life volumes, the fabricated design is actually, the one that uses very little dedicated tooling. That is the most cost effective. So, if you were going to make one of these plates, then it would probably be fabricated from laser cut sheet metal, which is what's been analyzed here. So much more interesting and maybe surprising is the fact that this fabricated design is most cost effective all the way up until this point right here. So it's, 750 parts or so. And that's where the extruded design comes into its own and becomes the most cost effective choice. So the extruded design, that remains cost effective up until about here, which is about, maybe 6,500 parts or so. And then that's where a casting with its more expensive tooling and, lower labor would probably be the best choice. So at our life volume of 2,500 parts, which is shown by this vertical line here, so an extruded design is what a designer should focus on in their design work. So that's the option of the three that they would want to take. So I hope you can see how the DFM concurrent costing software, it solves this problem. So it helps the designer identify the most cost-effective approach to satisfying their design objectives. And the software can do that before detailed design of a part has begun, when there's only very simple, common information that's available about a part. And that helps a designer very quickly figure out what type of part they should focus on designing.